Have you ever wondered why some mirrors make you look bigger, while others make you look smaller? Why do car rearview mirrors show a wider view, and why do dentists use special mirrors to examine your teeth? In this lesson, we will uncover the fascinating science behind curved mirrors and learn how they form different types of images. Before learning about curved mirrors, let us quickly revise reflection. Reflection is the bouncing back of light after it strikes a surface. According to the first law of reflection, the angle of incidence is always equal to the angle of reflection. This rule applies to both plane mirrors and curved mirrors.
Mirrors are of different types. The simplest one is the plane mirror. In this chapter, we focus on spherical mirrors. A concave mirror curves inward, while a convex mirror curves outward. Both follow the laws of reflection but produce different kinds of images.
A concave mirror has its reflecting surface curved inward. When parallel rays of light fall on this mirror, they reflect and meet at one point. This point is called the focus. Because the rays come together, a concave mirror is also called a converging mirror. A convex mirror has its reflecting surface curved outward. When parallel rays strike it, the reflected rays spread apart. If these rays are extended backward, they appear to meet at a point behind the mirror called the virtual focus. Therefore, a convex mirror is known as a diverging mirror. Imagine a flexible foam sheet with pins fixed vertically. When the foam is bent inward, all the pins point towards one common point. These pins represent the normals to the mirror. This activity helps us understand how normals behave on curved surfaces. A concave mirror is actually a small part of a large sphere. The center of that sphere is called the center of curvature. Any line joining this point to the mirror acts as a normal to the surface. A concave mirror is actually a small part of a large sphere. The center of that sphere is called the center of curvature. Any line joining this point to the mirror acts as a normal to the surface.
The midpoint of the mirror is called the pole. The straight line passing through the pole and the center of curvature is called the principal axis. The distance between the pole and the center of curvature is known as the radius of curvature.
When parallel rays fall on a concave mirror, they meet at the focus. The distance between the pole and the focus is called the focal length. For every spherical mirror, the radius of contortion is twice the focal length. In other words, R equals 2 times F.
Let's verify this with a simple activity. Hold a concave mirror in sunlight and place a small sheet of paper in front of it. Move the paper until you see the smallest and brightest spot. This point is the focus of the mirror, and the distance from the pole to this point is the focal length.
Unlike a concave mirror, a convex mirror spreads the reflected rays in different directions. These rays appear to from a point behind the mirror called the virtual focus. Therefore, a convex mirror is also known as a diverging mirror.
Convex mirror. Converse ility conflict mirror and takt. Flagsport mirror. Reflected rays diverge.
Let's verify this with a simple activity. Hold a concave mirror in sunlight and place a small sheet of paper in front of it. Move the paper until you see the smallest and brightest spot. This point is the focus of the mirror, and the distance from the pole to this point is the focal length.
When parallel rays fall on a concave mirror, they meet at the focus. The distance between the pole and the focus called the focal length. For every spherical mirror, the radius of curvature is twice the focal length. In other words, R equals 2 times F.
Now let's perform an experiment. Place a candle in front of a concave mirror. Move a white screen until a sharp image appears. By changing the position of the candle, we can observe different kinds of images. When the object is placed beyond the center of curvature, the image forms between the focus and the center of circumference. The image is real, inverted, and smaller than the object.
When the object is placed exactly at the center of curvature, the image also forms at the center of curvature. The image is real, inverted, and exactly the same size as the object.
When the object is placed between the focus and the center of curvature, the reflected rays meet beyond the center of curvature. The image is real, inverted, and larger than the object. When the object is placed exactly at the focus, the reflected rays become parallel to each other. Since the rays never meet, the image forms at infinity.
When the object is placed between the pole and the focus, the reflected rays diverge. Their backward extensions meet behind the mirror. The image formed is virtual, erect, and enlarged. Let's summarize the image formation in a concave mirror. The position and nature of the image depends entirely on where the object is placed. Remember these cases carefully because they are very important for examinations.
A convex mirror always forms the same type of image. No matter where the object is placed, the image is always virtual, erect, and smaller than the object. This is why convex mirrors are used as rear-view mirrors in vehicles.
Convex mirrors are commonly used as rear-view mirrors because they provide a wider field of view. Drivers can see more of the road behind them, making driving much safer. To draw ray diagrams easily, we only need to remember 3 special rays. A ray parallel to the principal axis reflects through the focus. A ray passing through the focus reflects parallel to the principal axis. A ray passing through the center of curvature reflects back along the same path. The first rule is very simple. Any light ray traveling parallel to the principal axis reflects through the focus of a contact mirror. This is one of the most important rules used in ray diagrams. The second rule is exactly the opposite of the first. Any light ray passing through the focus reflects parallel to the principal axis. This rule helps us quickly locate the image. The third rule is equally important. Any light ray passing through the center of curvature strikes the mirror normally. Therefore, it reflects back along the same path. The relationship between the focal length, object distance, and image distance is called the mirror formula. It is written as 1 by f equals 1 by v plus 1 by u. This formula is used to solve numerical problems. While using the mirror formula, we must follow the sign convention. Distances are measured from the pole. Distances measured in the direction of incident light are taken as positive, whilst measured in the opposite direction are negative.
Magnification tells us how much larger or smaller the image is compared to the object. It is equal to the height of the image divided by the height of the object. It can also be calculated using negative image distance divided by object distance. Let us solve a simple numerical problem. The focal length is -15 centimeters, and the object distance is -25 centimeters. Subtracting these values into the mirror formula gives the image distance as 37.5 centimeters. The negative sign indicates that the image is real.
Concave mirrors are used in many everyday applications. Dentists use them to see enlarged images of teeth. Shaving mirrors also produce enlarged images. They are used in torches, car headlights, and even solar cookers to concentrate light.
Congratulations! You have now learned the basic concepts of curved mirrors, image formation, ray diagrams, mirror formula, and magnification. Practice drawing ray diagrams regularly, and solving numerical problems will become much easier. In the next lesson, we will solve important SSC examination questions step by step.